Welcome to Frank Stajano Explains and to this Algorithms Xtra video for my course at the University of Cambridge. In the regular lecture about Quicksort, I went fairly quickly on the basis that my Cambridge students have already been exposed to Quicksort in the Foundations of Computer Science course that they took last term. Now, if you're not one of my Cambridge students, or if you are one and want to go in greater depth on Quicksort because you didn't quite get it the first time, then this video is for you. The Quicksort algorithm is based on the idea of pivot. One of the input values is selected as the pivot, and then all the values are either less than or equal to the pivot or greater than the pivot. There's no other way, and therefore we can put them into two classes: the ones that are less than or equal to the pivot first, then the pivot itself, and then the ones that are greater than the pivot. Within those classes we don't actually sort the values, we just leave them as they are. But it is the case that the pivot will be in its correct position, and all the values before it would never have to move to anywhere other than in the region where we put them. So let's see how this works in practice. We have an array that initially is the whole array from I begin to I end over there, and we choose by convention the last item to be the pivot. So this is the array we are given. From I begin to I end is where we are going to work on right now, and always the last element of the range we are working on is our pivot. If at some point we want to sort a subrange, for example this subrange, then we will move the I begin to here, the I end to there, and the pivot will be the last element of that range as we work through that particular subrange. So initially, we run Quicksort on an array A by running Quicksort subarray on the subarray of A between 0 and the length of A. So between 0 and the length of A. And so our pivot is going to be the last element in here. So what we do, since the pivot is this value 6, we run from the left using this pointer I left as far as we can to the right, growing a region of all the values that are less than or equal to 6. And then we grow from here with I right going towards the other end with all the values that are strictly greater than 6. So this works in this way. We put I left over here, and we go through here for as long as the values are less than or equal to 6. So is 3 less than or equal to 6? Yes, so we can move on by 1. Is 12 less than or equal to 6? Unfortunately no, so this one has to stop. So we now move from the other end towards I left, and so this now strangely our convention is always that an index points to the cell to its right, but in this case I right has to be a mirror image of I left, and therefore it logically points to the cell to its left, which in technical terms would be I right minus 1. So this is I right minus 1, this cell over here. So anyway, this cell that is logically pointed to by I right, and I do this because I want the region between I left and I right to be the one that I'm still working on, the one that's still unexamined. So is this 12 strictly greater than 6? Well, it is, therefore I can move this by 1. Is this 15 strictly greater than 6? It is, so I can move by 1. Is this 1 strictly greater than 6? It isn't, so I am stuck. So I was stuck here because this was not less than or equal to 6, and I'm stuck here because this is not strictly greater than 6. So my ideal is to move this I left all the way to the right and my I right all the way to the left until they meet each other, right? I will always keep I left to the left of I right, so it will always be the case that I left is less than or equal to I right. I'll never overtake, but I would like them to meet. I would like them to be equal eventually. So when I can't advance anymore, as in this case, because I'm stuck on this side, I try advancing on the other side. And if I'm stuck on both sides, then it means that this one is unsuitable for this region, but it means it must be suitable for this other region. And this one is unsuitable for this region, it must be suitable for this other region. So what I do is simply to swap them. I swap, oops, meant to move this. What's wrong with this? I swap this value and this value, because if 1 wasn't good for the right, it must be good for the left. If 12 wasn't good for the left, it must be good for the right. And now I try again. So now I move my left to the right as far as it goes. Again, is this value 1 less than or equal to the pivot? Yes, I moved it there on purpose, and so I can advance by 1. Now, is this value 8 less than or equal to the pivot? Unfortunately no, so I'm stuck again with left. Let's see if I can make any more progress with I right. Is this value strictly greater than the pivot? Actually it is, so let's move by 1. Is this value of 2 strictly greater than the pivot? It is not, so I am stuck again. So I am stuck, but notice that I have grown this region here with things that are strictly less than or equal to the pivot, and this region here with things that are strictly greater than the pivot. This will always be the case. The region between I begin and I left will always be made of things that are less than or equal to the pivot, and the region between I right and I end minus 1 will always be made of things that are strictly greater than the pivot. And I continue this process until I left and I right touch each other, at which point I will be left with only 2 regions which will be adjacent, and in the middle between those 2 regions I should have the pivot, although there isn't a space for it, so we'll see what we do at that stage. So let's continue this process, and let's now follow on the actual pseudocode listing that we have here. So what I do here is I am in the partitioning phase. I started with partition from I begin to I end, partition into those 2 regions. I am within this part of the code where my behavior is taking an array subrange a I begin I end. In this case it was the initial array, but this is repeated for smaller ranges as well. Let the last element in the range be the pivot. We did that. Partition the range into 3 regions containing respectively the elements less than or equal to the pivot, this one. The pivot, we'll have to put it back in the middle, and the elements greater than the pivot, this one we're drawing over here. And then return from this partition routine the index of the pivot, which will be a value between I begin and I end. In order to work, my precondition is that I begin and I end are included in the range of indices for this array, and also that I begin is strictly less than I end, and not just strictly less, but the distance between them has to be at least 2. If the distance between them were 1, then that 1 would just be the pivot, and there would be nothing else to classify, and so there's no point in partitioning if you only have one. You have to have at least 2 elements, one of which would be the pivot, then you have at least 1 element to put into one region or the other. And what we guarantee on exit is that the value that we return from this function, which is going to be an index I pivot, is such that it has partitioned the array into the 3 regions we promised. The left region from I begin to I pivot contains only elements that are less than or equal to the pivot contained in the position indicated by the pivot on exit, and all the values in the third region, I pivot plus 1 to the end, are greater than the pivot. This is at the end of the routine. I'm going to move the pivot not to the end here of this range, but to the place in the middle of the range which separates these two regions over here. So on entry into this partition, then I begin and I end have to be separated by at least 2 positions. I assigned I pivot pointer to be the last element in the range, and I set I left to I begin, and I set I right to I end minus 1, which is already the pivot. So throughout this body of the code, I preserve this invariant that I left is always going to be less than or equal to I right. I commented this out instead of just making an assertion to say, well, this is not just valid here, it's valid at all points. I could put this interleave this assertion between every 2 instructions, that would make the code unreadable, so I haven't. So while I left is strictly less than I right, while they have not met, these 2 pointers, what do? I have more nested while loops inside this outer while loop over here, and the inner white loop is the one that moves this pointer towards the right, while I left is less than I right, while I haven't reached this other pointer, and the content pointed by I left is less than or equal to the pivot, then keep moving, increment the I left, keep moving, and in this case it is not less than or equal to 6, so I had to stop. And then while I left is still less than I right, so they haven't met, and the one pointed to logically by I right, which is I right minus 1, so this one is greater than a pivot, then keep decrementing this one. But I can't anymore because this one is now not greater than the pivot. So I now get to this part of the code. If they still haven't met, these 2 pointers, then their distance is going to be at least 2. So this is a quiz for you. Why can't it be 1? Well, if they haven't met, it's going to be 2. And you have to figure out why. There has to be some explanation for this, which is non-obvious. But I won't tell you because I want you to think about it. So what you do at this point is you swap the 2 elements that are pointed to by our pointers that haven't met, because if they haven't met, then this is not suitable for this region. If it's not suitable for this region, it must be suitable for the other region, and vice versa for this one. And so let me do this swap. And at that point I can advance by at least 1 each as I go here. I left is moved by 1 and I right is also moved by 1 in their respective directions over here and over here. So this would be a growth of this region. And then I go back around this loop for as long as I left is still strictly less than I right, so they haven't met. So I run this loop again, this loop over here. I keep incrementing I left. So is my I left 6 less than or equal to 6? Yes, it is in particular equal, so I can move on by 1. Is this 7 less than or equal to 6? No, so I'm stuck again. Now I go in with this other pointer. Is this one strictly greater than 6? It is, so I move here. Is this 4 strictly greater than 6? It is not, so I'm stuck. So once again I now have to swap those two. I swap those two. I move my pointers by, move my pointers by 1 each. And I repeat this loop because I left is still less than I right. So is this value 8 less than or equal to 6? No, so I'm already stuck here. Is this value 7 strictly greater than 6? It is, so I can move this one by 1. Is this value 4 strictly greater than 6? It isn't, so I'm stuck on both sides, so I can swap these two. Finally getting there. And I can move each of these by 1. So now pointer, I'm into this small inner loop again. This value pointed by I left, is it less than or equal to 6? It is not, so I'm stuck with this one. With I right, my other loop, can I move on? Is this one strictly greater than 6? It is, so I can move this by 1. And so at this point within this loop, while I left is strictly less than I right, blah blah, and now I can't iterate through here anymore because I left is now equal to I right. So I finish this loop because I am now kissing I left, and so I go into this other if statement. If I left is strictly less than I right, and it's not because they are in the same position. So I skip this if statement and I go back to my main while loop. So if I left is less than I right, well, it's not, so then I exit my main while loop as well. So it looks like I'm at the end of this partitioning procedure. What I do is I swap I right and I right and I pivot. So I right is this one and I pivot is this one. So what I'm doing is I'm basically saying I have completed a region of things that are all, as I was saying here, I begin to I pivot are, well, I pivot is going to be here where I have these two pointers. I'm going to stick I pivot here in a moment. This region is all made of things that are less than or equal to the A pivot, to the pivot. This other region from one more to here is going to be made of things that are strictly greater than I pivot. So actually this was this region here, from here to here. But what I'm doing is I'm going to make space here for the pivot, and this value, which is in this region and therefore it is strictly greater than the pivot, can go and take the place left by the pivot, because then it will be this region that is strictly greater than the pivot. The pivot's going to be here, and then all these things are going to be strictly greater than the pivot. So I'm trading places between this one and this one, so that this value, which was strictly greater than the pivot, goes in here. That's a fine place for something strictly greater than the pivot, and the pivot moves here in the middle. So let me do that, and that would be this line here. Swap the I right and I pivot. And actually, if I were to edit this listing, I might change this I right into I left. Although at this stage they are equal, I could put an assertion that by now they are equal. But anyway, it is logically clear for me to say I left, or maybe no. Actually, it depends how you choose to reason about it. If you reason in terms of I want to have my cell pointed to by the pointer in the way we usually do, then it makes more sense to say I left because it's one. If you want to say actually that's the smallest value of the region between I right and I and -1, then it makes more sense to say I right. So after all, I won't change it. I will just say I right because I right points to the bottommost element in this region that I just created. So anyway, let me swap this into the position of the pivot and take the pivot and bring it here. So at this point I now have the pivot, which is let me highlight the pivot in red. Pivot is here, and the pivot is definitely in the correct place because anything that is less than or equal to the pivot is in here, and anything that is greater than the pivot is in here. Even though these things are not in order, they can't move the position of this 6. The 6 will have to be here. So at least one place has been now put in the correct place. So now I put I pivot equal to I right over here, and that's going to be the return value. Oops, I think I should do something to make them stick so that it's impossible for me to move these things by accident. Lock this thing down, and if I can I will also lock this other thing down so that if I make an operator error, at least I won't keep moving these things around by mistake. So that doesn't seem to have worked. Okay, no, lock. Okay, I thought I had locked you, bastard. This, lock, stay locked, go away, click. Alright, where was I? Okay, I was going to return the value I pivot. So this is the return value from my partition routine, and partition had been called by this line here, which said, okay, partition the region from I begin to I end, and it returns the pointer I pivot to here. So what I do next is I recursively quicksort the subarray from I begin to I pivot, this first region, and then I quicksort the subarray from I pivot +1 to I end, this other one. So you see, I fixed one item, and then I recurse into two regions, the union of which is smaller than my original array. So I'm guaranteed to make progress at every run of this. Of course, inside each of these there's going to be another call of partition on that particular range. So I won't continue until the end because otherwise it gets seriously boring. But if I go once into a subroutine, what happens? If I quicksort subarray I begin I pivot, then my I begin is here, the I pivot is here. So this means that as I enter this routine over here, then my I end gets assigned by the procedure call to this. Okay, so these things are uninitialized at the moment, this 1, 2, within the routine, and so I'm here where 0 is less than I begin. I think this is a mistake. It should be less than or equal to I begin. So this assertion is wrong. I should fix that. Less than or equal to I begin. Let me get a fine pen for this. Less than or equal to I begin. Alright. I begin is less than or equal to I end. I end, yes, I assigned I end to be here. And yes, this is correct. And I end is less than or equal to length of A. I'm saying that they are within the range of values, the range of indices for the whole array. All right. So now if I end minus I begin is less than 2, so if the subarray is of length 0 or 1, then there's no point to try to sort it, but in this case it's of length 1, 2, 3, 4, 5, 6, so there is some point in sorting it. So my I pivot is going to be what is returned by partitioning a I begin I end. So I go into this other part of the code. I partition from a I begin I end, and so these get reassigned to these positions, and so the distance between them is at least 2, yes. I pivot gets assigned to I end minus 1. So the last element of this subrange is going to be my pivot 4. 4 is going to be the pivot for this round. I left is initialized to I begin, and I right is initialized to I pivot. I think that yes, that's where we want to be. And so the range that we want to partition is this one less than what we are given, and this last item is our pivot. So we run the by now familiar procedure with 4 as our reference. So is this item 3 less than or equal to 4? Yes, so we can move on. Is this one less than or equal to 4? Yes, so we can move on. Is this item less than or equal to 4? Yes, so we can move on. Is this item less than or equal to 4? No, so we have to stop this one, but we can give it to go with this other one. So now, is this strictly greater than 4? No, so we are stuck with this one as well. So we are stuck on both sides, so it's now time to swap them. So we swap the 6 and the 4, and then we can move each of these two pointers by 1. And at this point they are kissing, lovely embrace, which means that we have finished our major loop over here. And so we swap the I right with the pivot, so it's this one and this one. So we've created two regions, one region of things that are less than or equal to 4, and one region of things that are strictly greater than 4. And so we swap this last element, we swap this element, the first element of the things that are greater than 4, with the pivot, so that the pivot is between the two regions. This pointer sometimes grabs something other than what I wanted to grab. Okay, so this goes here. Right, so now I'm going to set the I pivot to be I right, and the value I'm going to return as the pivot is this one. So this one has now been put in its final resting place, and I can now exit from this partitioning procedure. So it was the end of this, and now I would have to quicksort recursively this subarray, and when I'm done with that, quicksort recursively this other subarray. But this other subarray has length 1, so once I get into here, you will see that I have the shortcut of just returning it as already sorted. So this one's already sorted because it has nowhere to go, because it's jammed between two things that are fixed. So this one will be a quick one to do, and this one will proceed in the usual way, and then I will get back to doing this one, and so on and so forth until I get to something as small as this, and then I can exit. So that's it for the quicksort. Now I have once given this presentation in presence of Tony Hoare, who invented quicksort, and he said this was a beautiful and clear explanation. I was very proud of that. Maybe one day I'll dig out the video of when he visited. But I want to highlight that in your wonderful textbook, Cormen, Leiserson, Rivest and Stein, a slightly different version of the quicksort algorithm is presented, in which the two regions don't grow from the sides inwards, but grow from the left, one on top of each other. Let me just demonstrate this quickly using the same numbers as in the example in the book to make it easier for you to follow through. The translation is not difficult, but anyway, here's the idea. You start with the two regions collapsed against each other here at the beginning of your array, and your last element is the pivot, as we did before. So this part contains the pivot just because it's the last element. So you compare things with 4, and if they are less than or equal to 4, then they fit in the first region. So 2 fits in the first region because it is less than or equal to 4. The next value, 8, fits in the second region. Next value, 7, fits in the second region. Next value, 1, should fit in the first region, but I can't expand this to include it. So what I do is I swap this 1 with the 8 that was the bottommost element of this top region, because if I do that, then I can expand the bottom region. This one gets translated to here, and everybody is happy. This 3 is again one that can't fit in the top region, but I can swap it with the bottom element of the top region and expand those regions. So if I put it in here, I expand this one and this one. Now this 5 instead is greater than 4, and therefore it fits in the top region, so I can simply expand that without having to swap anything. And the 6 again is greater than 4, so I can expand the top region without any other special things. And I finish with 2 regions, basically like in the other version of the algorithm, where these ones are less than or equal to the pivot. These ones are greater than or equal to the pivot. Note that they put the equal sign on both sides. Not that it makes a huge difference. And at this point, I swap the bottommost element of the top range with the pivot. So, so that I now have the pivot in place, and then 2 regions that I will have to resort recursively. One here and one here. One here of things that are less than or equal to the pivot, and one here of things that are greater than or equal to the pivot. And the rest is the same as we did. So the difference is just that the 2 regions grow from the left on top of each other, and the swaps happen between the beginning and the end of the top region. Strictly speaking, the first element of the top region and the first element outside the top region, whenever there's a swap. And with that small detail of change, the rest of the algorithm is the same. There's many other variations of quicksort that people have come up with, especially to do with how to choose a pivot so that you don't run into bad cases. For example, if your input is already sorted, then your pivot will be the greatest element, and so everything will be in the first region. There will be an empty top region. That's independent of whether you grow the regions from the left or whether you grow them from inside out from both sides. If your last element is always the greatest, then you will always be stuck with one region that is empty, and that will make your recursion go very poorly, because you will be dividing as unevenly as possible at every stage, and so you will end up with quadratic costs instead of n log n costs. And so people have applied a lot of ingenuity in devising alternative ways of choosing the pivot so that it is less likely that you will hit upon the bad case. But it is impossible to eliminate that case because given all the permutations of the input, some of them will have always the greatest value selected as a pivot in the tree of choices that you have to make. It's just that the case of the input already being sorted is somehow more probable than just any random input, and you want to avoid the case where running Quicksort twice the second time means the input was sorted and the second time is guaranteed to be quadratic. So choosing the pivot in some other way, including choosing it at random, might minimize the chance of that happening, just because having the input, not all possible permutations of the input are equally probable, and the one where the input was already sorted is somehow more probable than the others in practice. But it doesn't, and no choice of pivot can eliminate the possibility that some input will exist that will cause the quadratic behavior.